Hi, welcome to the first session of a series of lectures on countable and uncountable sets. We will be mainly focusing on countable sets, prove various results, and finally we will talk about uncountable sets and prove R is uncountable, and also we will prove Cantor's theorem. Okay, so we will get started. Right, the basic reference is a book by Ajit Kumaresan and Baba Sharma, a foundation course in mathematics. Okay, I will be trying to follow as much as possible. Usually I don't follow any book, that's a problem. Okay, let's get started. But let me ask you a question. All of you will know the word, right? Calculus, differential calculus, integral calculus, residue calculus, and calculus of variations, calculator. Yeah, and what is the real meaning of the word calculus? You'll be surprised. Have you heard the medical terminology? They will talk about kidney stone, but among themselves, doctors will refer to as renal calculus. So calculus actually means stone. Okay. So why did it then we started saying calculus, calculation, calculator, etc. That is because look at the primitive man at Stone Age, and he has not learned the numbers 1, 2, 3. He has not learned how to count. But he is living in a cave and he has a cattle, perhaps sheep or cows. Okay. Then he lets them in the morning to go on graze and they brings them back to his cave in the evening. But how does he know the cows which we went return? All of them return. Okay. One ingenious fellow thought of a trick. What did he do? When he was letting out, one one cow goes out, then he keeps a stone out. Another goes, another stone. Another cow, another stone, or another sheep. Okay, he keeps. Okay. Then when comes back, he lets one. Okay, one cow comes, one stone take out, etc. Then he finds if they match, when all the comes come, he has accounted for all the stones. Then he thinks that all the cattle has come back to his cave. Is that clear? So, without knowing numbers, what he did was he set up a bijection between the set of cows and a set of stones. Do you understand that? That is why the word calculus came about. And that is the idea which Cantor understood well, and he started thinking about how to count infinity in different ways. Okay? Try to think about this. We'll get into the subject now. So as usual, yeah, this is my channel, and anything related to videos, please write to this email ID. Do not use my other email ID. Okay, and you can download the list of my videos which are available on this channel from this set, and they are arranged according to order. Okay, topic wise, so it will be easier if suppose you wanted to learn about topology, or you want to learn about metric space, or you want to learn about several variable calculus, or you want to talk about convergence of functions. Okay, they will be according to topics and graded way, so that it will be easier, because YouTube does not show them in proper order, so you may not know how to watch. Okay, right. Now, as I said, this is countable and uncountable set session 1, and the references this book by three of us. Okay, right. Now let us get started. So the first idea is due to Cantor. What did he say? Let us try to understand this idea. He says, intuitively, I have two sets x and y, right? I say x and y have the same number of elements. Okay, this is, don't worry about the meaning. If there exists a bijection, from X on to Y. Remember what I said about Stone Age man? Okay, he did not know how to count. So what he did was he has a number of cats, some finite set of cattle, and he had a finite set of stone. He matched them. So if there is a bijection, he knows. If if one stone remains, that means one cattle is missing. Right? That's how he found it. Or if all the stones are over, but one more cattle is coming, few more cattle is coming, then he knows they are extra. Okay, he's lucky. Do you understand this? So now he want to talk about even an infinite set the same thing. Okay, let us first start with finite. Okay, this has to be a separate topic on its own. Let us do that. Okay, suppose X is a set. When do I say it's finite? Okay, let us look at in to be the initial segment 1 to n. This is a subset of natural numbers. Okay, right? So when I say X is finite, either X is empty or there is an 1-1 map of X into some in. Okay, you understand that? This is a 1-1 map into this. Then I say it is a finite set. Now the important thing is I want to say what is the number of elements in a finite set. What is the obvious thing? Obvious thing is okay, if there is an n in natural number, okay, if it is non-empty. Okay, so that there is a bijection. Then what would I like to say? I would like to say n is the number of elements in the set. But being a mathematician, you should know, one has to ask a question. Maybe there is another thing which goes to im, where m is also an element, n is also an element of natural numbers. This is n, this is m. Okay. Then what is that I would like to say? If such, okay, if x is a finite, if I have a bijection of x into in as well as bijection of x into im, then I want to say m must be n. Therefore, the number of elements in a finite set is fixed. Okay, this is a theorem, non-trivial result. Okay, we will look at a proof later in some other video. Also, it is found in my book, in the book which I mentioned. Okay, so number of elements is uniquely defined. You will see why it is needed. Suppose I have a very huge pile of, let's say, chocolates, okay, or coins. I want to count them. Okay, I may count it to be 222 and you may count it to be 219. Another fellow will say 223. You understand? There is a possibility. There is a huge pile of coins. We may make mistakes, but all three of us will know there is a unique number. Right? This theorem says you are right. There is a unique number. Okay. So F is a counting. F counts number of elements in X. G also counts the number of elements. Okay. This counting process may yield two distinct numbers n and m, but that can never happen. That's what the theorem says. Okay. Pause. Understand the theorem. We are not going to give a proof here. It has to wait. Am I sharing the thing? Yeah. Okay. So let us go back. Now x and y may be any sets. Okay. When do I say x is an infinite set? If x is not finite. Later we will say a much better definition for infinite set. Okay. Later there is a much better definition. We will see a glimpse of that now immediately. So when I say x is an infinite set, okay, it only means x is not empty and x is not a finite set. When I say it's a finite set, remember x is empty set is also finite. For empty set I will say number of elements is 0. So this is a notation. If x is finite, we write by norm mod x, which means the unique n. The unique n said that there is a bijection of f from x to in. That is called the number of elements. Okay. Now for infinite set also Cantor said this is Cantor's proposal. Okay, x and y have the same number of elements. if there is a bijection f from x to y. Okay. Now modern terminology, number of elements, they replace it by the same cardinality. This word is replaced by this. They have the same cardinality here. Okay. When Cantor proposed and showed some examples, okay, mathematicians were really frightened. Okay. They did not accept, they could not. Why? We will see a very simple example. Suppose let us take n. Okay. All of us intuitively know this is an infinite set. Right? Okay. Now let's take y equal to 2n, that is all even integers. 2, 4, 6 and so on. Now there is a bijection f from x to y, namely f of n equal to 2n. This is a bijection. Right? So Cantor would have said x and y have the, assume he did not use the word cardinality at the time, then you will say x and y have the same number of elements, but you can see how repulsive it would have been, okay, when he proposed, because we know 2n is essentially half the size of n. Do you understand that? So they did not want to accept it. Okay, n and set of even integers have the same number of elements. In fact, I can even make it worse. Suppose let us look at p a prime. Okay, p in n is a prime, right? Now let's look at the set, okay, y, or let us say z equal to p power n as n varies over natural numbers. Then you can see there is a bijection of x, which is natural number, to z, namely n goes to p power n. This is a bijection, right? Why? It's a 1 1, okay, on 2 because of everything. It's 1 1 because if p power n equal to p power m, that means p power n minus m is 1. That means n minus m must be 0 or n equal to m, right? And it's on 2, that's very clear because every element in z is of the form p power n, right? Now suppose p is a very very large, the number of primes is infinite, therefore if you take a very very large prime, this will be very intuitively very very small. Sorry, this is z, this is z, okay, not z, okay, if you want call it a, okay, okay, a will be very very small. Subset of natural numbers, but it also has the same number of elements as n. They have the same cardinality. Yeah. Let us make it little more impressive, so that I want you to think about such things. Okay, because these kind of shocking examples will make you sit and try to understand. Okay, accept our hereafter we will say x and y have the same cardinality if there is a bijection. That's our thing. Okay, intuitively it may say the same number of elements, but because of these examples it is better to use the word cardinality. Okay, let us look at this. Suppose Pn, okay, the set of infinite set of primes in n, right? Okay, now let us look at for each n, let me look at a n to be Pn to the power k running over a natural number. Now notice that an is not equal to am. Yeah, because this is a different prime. This, for example, when p equal to 2, this will be 2 power k. When p equal to 3, it will be 3 power k, right? So this may be something like 2 power k running over n, and this will be 3 power k running over n, and 5 power k running over n, etc. Okay, now each one of this, we know that each n, okay, there is a bijection. Okay, they have the same cardinality. Okay, right, there is a bijection f1, right? Now notice that if I look at union an, okay, as n varies, okay, this is still a proper subset of n. See, I have ans. How many ans are there? Infinitely many ans, because the set of primes is infinite. and they are pairwise disjoint, right? And this union is proper because if I were to take something like 2 squared into 3 or 2 squared into 3 power 4, okay, these things are not going to be there in their union. So still is a very small subset. Okay, so N has infinitely many subsets so that each one of them has the same number of elements as M. That is, each one of them has the same cardinality of that of M. Do you understand that? Okay, pause, review, proceed. Yeah. Now let's look at some examples. Let us say Z, set of integers, and let us look at N. So I want to say they have the same cardinality. Hereafter I will use the word same cardinality. So what does that mean? I have to set up a bijection. How will I do that? So let us write it, then you will see. I have 1, okay, so let us say 0, 1, 2, 3, etc. minus 1, minus 2, minus 3, etc. And I have 1, 2, 3, 4, etc. Right? So what I can do is I can use set up this. Let's send 0 to 1 and 1 to 2 and minus 1 to 3 and 2 to 4 and 3 to minus 2. Root 2 minus 2, this should be 5. You understand? So you see the pattern. So where the 1 goes to 2, 2 goes to 4, and where do you think 3 will go to? 3 will go to 6. Right? So I am thinking of the function so that, okay, from Z to N, so that f of 0 is 1 and f of N is 2n for n in N. Then let us look at f of minus n for n in N. What happens? Minus 1, where did it go to? It goes to 3. And minus 2, it went to 5. Do you see a pattern? Minus 3 will go to, now where do you think it will go to? It will go to 7. Right? So what is our pattern? So 1, take minus of that is 2, add 1, you got 3. Minus 2, take its absolute value 2, multiply by 2, you get 4, add 1, 5. Therefore it goes to 2 times mod n plus 1. See, now I have a map. Right? Okay. Now is this 1 1? Is f1 1? Is f1 2? These are very easy to check, but for the first time we will do that. Okay. How do I know whether they are the same? Yeah? Right. How do you do that? Is 1 1, is that clear? Suppose f of n equal to, let us say, f of x equal to f of y. Right? Okay. If x is 0 and y is not 0, then this fx is not equal to fy. That's clear? Because f of x is 0 and what is f of y? It is either 2n or 2 mod n plus 1. So both are already greater than 1. Do you understand that? Yeah. So f of y will be either 2y if y is positive or 2 times mod y plus 1. So in any case f of y is greater than 1. Strictly greater than 1, right? Therefore when, so the next thing is, if x and y both are positive, then also it is clear because f of x equal to 2x, f of y equal to 2y, and if x is not equal to y, then fx is not equal to fy. Right? So next, let us look at, suppose one is positive, other one is negative. Then remember fx is even, whereas f of y is odd. Look at that, 2 times mod y, right? Therefore we conclude f is 1 1. Pause, review, proceed. Now I want to know whether it's okay. Is f on 2. So let us start with some natural number n, right? If n equal to 1, then f of 0 is 1. Okay. So let me assume n is greater than 1. Now if n is greater than 1, then f of okay n, either it's of the form 2n if n is if capital N is even, or it is of form 2n plus 1. Remember n is greater than 1, therefore it has to be this. Okay, 2 is already taken care of, therefore it has to be with n greater than in natural number. It's not 2n minus 1 of the form. Do you understand that? This n has to be greater than 1, greater than or equal to 1. Why? If n is 0, then that means if n is 0, that means is capital N equal to 1, but I am saying n is greater than 1. Therefore, this has to be this. Is that clear? N is odd, greater than 1, therefore the positive stop is 3. Are you following? Then what do you think I will do? If this happens, then f of n is n. If this happens, then f of minus n is n. Is it okay? Therefore, f is on 2. Pause, review, proceed. Yeah? Right. Now let us look at a very simple example, another simple example. Suppose I take 0, 1 and let me take something like 0 to, let us, huge number, okay, 2 to the power 20, 23. This is my x, this is my y, okay. Just do not worry about, think of some, okay, some r where r is positive, okay. Then I say f and x and y have the same cardinality. See, 0 1 may be this, 0 r may be huge, okay, still r is going out to my right, okay, anything. That's very clear because I can take f of x equal to r times x. Then this is a bijection. Okay. More generally, if you give me any two interval a, b, and c, d, okay, there is a bijection f. They have the same number of elements. How do you prove that? Okay. This, if you had seen my foundation lectures, you would have seen. But easier thing will be, let's assume that a and b, everything is positive. They are all in the first quadrant. Okay, this is my a. Okay, maybe okay. Let me say, this is my a, and this is my b, and this is my c, and this is my d. Right. So what is that I want? I want a to go to c. Right. That means this is ac. And this b I want to go to d. This is bd. Right. Now look at the line joining this. Okay. You can write down the formula for this. Okay. Some y equal to something. You know how to write it, right? So that will be the function you want. Okay. I don't want to do this. It's a very trivial 11th standard coordinate geometry. You should do it. Okay. Okay, come back and try to see the excitement and the kind of confusion about, let's say, about 150 years ago people would have had. Okay, you see that very small subset has the same number of elements as the original set. And similarly, I have an interval 0 1 its unit length. Now you take some interval of length, something like I'm on 2 million, 2 trillion length, but they also have the same number of points in the line segment. You can see that people would have been really shocked. How can they accept? It certainly has more elements, right? If I take 0 1 and 0 to 2, there is 1.5. It has extra element. Okay, these are the things they would have. So till they learn to accept, okay, that is, we went back to the logic of a stone man. Okay, they have the same number of elements, that is, they have the same cardinality, means they have a bijection. Please understand. I had given you some more examples. I will give one more example and stop this lecture with that. Now let us look at natural numbers n and look at natural numbers n cross n. These are ordered pairs mn, right? And I claim they have the same number of elements. Okay, that is n and n have the same cardinality. Okay, now how will I prove that? That means I want a bijection. So I am going to set up a bijection from n cross n to n. I want to think of a bijection. How do I do that? That is in such that f of mn should be different from f of rs. So if m and n are not equal to rs, what does that mean? That means either m is not equal to r or n is not equal to s. If one of them is not equal to the corresponding one, then the images must be distinct. How will I do that? This is where some basic ideas about number theory helps us. Now suppose I start with any natural number n. Do you accept it? I can write it as, let me write a natural number, let us say, okay, n. I can write it as 2 power r into some let us say yes, so that yes 2 does not divide s, that is s is odd. Okay, because by prime factorization I can write as some 2 power r into product of various other primes, but they are all odd primes, therefore the product will be odd. You understand that? So I can always write it. Do you understand this? Yes, that is what I want to make use of. Okay, this is what I want to set the bijection, or I may or may not be able to do it, but you will see how I plan to do it. This is the trick I want to do. So what I want to do is I will define f of mn to be equal to 2 to the power m and 2n plus 1 I want to define. Right? Now do you see there is this is a basic idea. I can always write it. I have written it. Okay. Now there is a problem because remember f of mn, m and n are greater than or equal to 1. Therefore this will be, at least if it is 1, this will be 2 to the power 1, this will be 3, therefore it should be greater than or equal to 6. So it may not be a bijection. Are you following? Yeah. So I try to change this. So see, this could be, for example, this r could be 0. If I take 3, then it is going to be 2 to the power 0 into 3. Right? Therefore I should allow r to be 0. And similarly if I take 2 squared, then it is going to be 2 squared into 1. This is same as nothing, right? That means here I should be able to write again. Yeah, that means I should allow n to be 0. Therefore it will become 2n plus 1 will be 1. Are you following? Please think. So what is the way out? So let us take z plus grad z plus 2z plus. Right? What is z plus? Z plus is n union 0. Right? Right. But again there is a problem. What is the problem? If I start with something, okay, m and n, you can see m may be 0, n may be 0, but this is already 1. But I want it to be a bijection, that means it must be onto. Therefore 0 should be there. Right? 0 should be in the image. So I won't get 0 with this method. So again what do? I want to get 0, so I will again modify 2 to the power m 2n plus 1 minus 1. I do not know whether it's going to work or not. You see that? The trick is I understood this, so I want to exploit this trick, this observation, to get a bijection. So how am I going to do that? Okay, this is one thing which I have got. Still I do not know whether it will work. Let us see. Okay, is it on? Suppose I take f of rs, therefore let us assume mn is not equal to rs. Okay, then I want to say these are not equal. 2 to the power or 2s plus 1 minus 1. So if they are equal, that means these are equal, that means 2 to the power m 2n plus 1 must be 2 to the power r and 2s plus 1. Right? Now notice that this representation of any number is unique. Right? That is, if I start with any natural number n x and write it as 2 to the power something, okay, this is unique. You follow that? If these two numbers are equal, that means 2 to the power m equal to 2 to the power r, therefore m equal to r. And cancel this, that means 2n plus 1 equal to 2s plus 1, therefore n equal to s. So if this happens, this implies m equal to r and n equal to s. So pause, review, proceed. I hope I am sharing. Yeah. You understood that? Therefore it is 1 1. Is it on to? So if it's on to, what do you think I have to do? That is, you give me an x or capital N in natural number, sorry, z plus. Okay, now whether 0 is there? Okay, first let us see whether 0 is there. Z plus cross z plus. Yes, because 2 to the power 0 into 2 0 plus 1 minus 1 will be 0. That is, f of 0 0 is 0. Is that okay? Right. So let me assume I start with an n which is in n, because I have to look at its on to, but this is n union 0 and I have said 0 is already in the image. So I only have to prove every element of n is there. Okay. So start with n, then what I have to look for 2 to the m and n, f of m n. I have to choose an m and n so that this is equal to n. Right? But that is very easy because n is a natural number, right? Therefore I can always write it as the form 2 power r into 2 power s plus 1. Okay, right? By prime factorization I can always write it like that. Right? Therefore I know what is m. Okay, my m I have to choose as r, and s, n has to I have to choose as s. Yeah. Of course, I use prime factorization. You may say that if 1 is there, only prime factorization talks about natural numbers which are greater than 1. Do you remember that? So, okay. So, if n equal to 1, we already proved it. Okay. Let us also suppose n equal to 1. What do I want? 2 to the power n, 2n plus 1. Okay. Sorry, minus 1. Sorry, I am very sorry. I got carried away. F of mn by definition is 2 to the power m, 2 power n plus 1 minus 1. This I want to be n. That means 2 power m, 2 power n plus 1 must be equal to n plus 1. But this n plus 1 I can write as 2 power r into 2s plus 1. Right? Therefore, my m by uniqueness must be r. There is no doubt about it. Yeah? You follow that? And my n has to be, yes. Right? It's not 2 power r 2 power s equal to not n but n plus 1. Are you following? So we proved f is on to if n is greater than 1. If n equal to 1, that again I know. What is that? f of 0 0, right? F of I want 2 to the power m plus 2 power n plus minus 1 equal to 1. Therefore 2 power n plus 2n plus 1 must be equal to 2, right? That means my n equal to 0 and m equal to 1. That is f of 1 0 is 2. I hope I did it correctly. Just make sure. 2 power n, yeah, n equal to 2. This will be 0. Yeah, right. Okay. So we have proved f is a bijection. Yeah. So we will prove a lot of other things. We have not yet defined countable sets, etc. I only prepared the ground, okay, for number of elements. So intuitive notion of number of elements. Cantor's precise definition is there is a bijection between those two sets, and it is a very shocking definition, okay, but it coincides in the case of finite sets. In the infinite sets, okay, It caused a lot of turmoil, confusion, non-acceptance, disbelief, incredulity among his contemporaries. Even big mathematicians had problem, great mathematicians. Later, slowly, whenever a very new idea comes, there is always some kind of resistance, right? This also had something similar. But slowly they understood the kind of pure logic in that and appreciated that. Okay, please go through the examples, and some of the examples I had given are not usually done in the textbooks, in our book, but go through these things, you will really appreciate. Okay, we'll meet again. Take care and stay safe.